So for the steady state errors, so the concept is I have an input here. And this is whatever my input is. That goes to a summing junction. This is my transfer function. Most of the time, we've done a unity feedback. So H is equal to 1, but it doesn't need to be. And what we've done is we've opened the loop. So if you go back, I can't remember what specific class it was, but the concept is we are opening the loop to find the difference between.
All I can see is your exam 3 review. I can't see what you're writing.
Oh, I must have shared the wrong screen. Sorry about that. Thought I had switched that over. Is that the right screen now?
Yep.
Okay, sorry about that. So let's go back to that just briefly. So my input is going to my summing junction, and that goes to my feed forward design, my G term. And then in most cases, we've done a unity feedback. And the reason being is if we actually want to calculate the error is equal to the difference in what we want, or what we have, I should say. Want minus what we have. That is technically what the error is. So if you think about the concept of your cruise control, you set it at 65 miles an hour. And if it's 55 miles an hour for whatever reason, then your error is comparing the desired 65 versus the actual of 55. And so normally we treat the error as being unity because this is what we have and this is what we want. So we're trying to compare the output to the input, but there are some systems where we don't have a direct comparison to have, like the 65 mile an hour case, we're directly comparing it. It might be that our input is 5% and then the output is a certain flow rate or something like that. So we typically will assume that we have a unity feedback, but it doesn't necessarily need to be. If it's definitely where H is equal to 1, then we actually will have error. If H is not equal to 1, then what we have is not an actual error. It is I think it was called the RA. It's the converted error, essentially, is what we're looking for. So we have to make some adjustments. But in either case, what we're comparing is the difference between what we want and what we have. Okay. So if we open the loop, and this is where it's really important to open the loop, here's G, and here is H. And again, this is opened. Our transfer function is we're looking for the transfer function between the input and, whoops, this is minus, and this value that is fed back over here. So what we see is if we take our input, multiply that by G, then by H, we're going to get to this point here. And the difference is it's going to be equal to our, we'll call it our error signal. And we're looking for the difference between these two. So all we need is the transfer function G times H. So if you recall, we have two transfer functions. We have an open loop transfer function and a closed loop transfer function. For all systems that have feedback, our open loop transfer function is G times H, and that's it. Our closed loop transfer function is G over 1 plus GH, right? That's the importance. And I think what was tripping up a lot of people on this homework is they were going and getting this transfer function. But remember, what that gives me is it gives me my output over my input. So when I multiply that by my input, then I end up with my output. But I'm not looking for that. I am looking for steady state error. This is in the time domain, right? The equivalent would be in the Laplace domain of E of S. Not out of S, but E of S. So I can't use the closed loop transfer function to get my error or my steady state error, I have to use the open loop gain. All right. So hopefully that adds a little more clarity to how to do the homework problems. Let's take a look here at number 3. So the first thing I have to do, so let me go ahead and copy this and paste it into the whiteboard. And then move that over here. Okay, so I've got to go ahead and find G times H. So the first thing I'm going to do is find G, which is in the feed forward path. So it's 4 plus 10 over S. And these are in cascade, so I multiply those together. If you remember from our block diagram section where we did block diagram math, elements are in cascade with each other, multiply. So S plus 2 all over S squared plus 4S plus 8. Now, this is not the cleanest thing. So we'd like to do is put that under a common denominator. So we have 4S plus 10 all over S times S plus 2 over S squared plus 4S plus 8. And then we can combine those into one block. Oops. Or not one block, but one simplified expression. We have 4S plus 10 times S plus 2 all over S times S squared plus 4S plus 8. That is our feed forward gain for this particular system. Now our feedback one is just equal to 0.05 over S plus 4. Our open loop transfer function. So our transfer function, that is open loop, which we've already defined as G times H, which is 4S plus 10 times S plus 2 over S times S squared plus 4S plus 8. That also has to be multiplied by 0.05 over S plus 4. So simplifying that down, let's see. Can I distribute the 0.05? I guess I'll just include it in here so it doesn't get lost. So it's 0.05 times 4S plus 10 times S plus 2 all over S times S squared plus 4S plus 8 times S plus 4. Now, at this point, you have the option. You can go ahead and decide if you want where you can factor this out using a quadratic equation if you want. But hopefully with some realistic approach, you can see that I'm not going to get a pole at S equals 0, because if I factor this out, there's no way to get an S term in there. I'd have to have some sort of a multiple of S in front of the 8 or multiply by the 8. So now to do system error, I have my open loop transfer function, which means I have to parse through and figure out the system type. So what is the system type for this particular system? What is the system type?
Is it a type 1?
Yeah. So system type, if you're not sure, is the number of poles at S equals 0, or another way to say that is the number of integrators, or if you still don't like that, or it is the number associated with the S to the number term. So in this case, we have S to the 1, which implies a type 1 system. Okay. So we had to do a little bit of work to figure out the system type that this has, type 1 system. So now we're ready to proceed and figure out, okay, I know what the system type is. Now I've got to go ahead and figure out the error. So now I've got 3 inputs. I've got a unit step, a unit ramp, or a unit parabolic. And I said units, but they don't actually have to be units. It could be multiples. It doesn't necessarily matter. So for the input, here's where I've got to go ahead and start to specify. So this is my constant. Okay. So my constant here for the unit step is a position constant. So that K sub P is equal to the limit as S approaches 0, G times H. So if you recall, I always had a limit function of G times H, not G over 1 plus G8. It is the open loop transfer function there. So that was going to be equal to my constant. And that's the value that I have here. For our unit ramp, it's a velocity constant because I'm multiplying my open loop transfer function by S. So if my K sub P is the limit as S approaches 0, G times H, if I multiply my position constant by my value of S, or my variable S, I'm taking one derivative of that position constant, which means I end up with the velocity. So the derivative of K sub P is K sub V, and that's how I get my velocity constant. Lastly, I have my acceleration constant, which again is taking the limit as S approaches 0. Now I have to take the second derivative of my position constant to get the acceleration, or I multiply it by S, and then I end up with that value. Okay. So let's take a look at any old system, or we're going to look at this specific system. So let's zoom out a little bit. So I'm going to actually do the full-blown math and see what I end up with. So if I take the K sub P, which is equal to the limit as S approaches 0, G times H, so it's 0.05 times 4S plus 10 times S plus 2 all over S times S squared plus 4S plus 8 times S plus 4. What I see is that when S approaches 0, all these terms that have an S that go to 0. So I have a 0 here and a 0 here. So I end up with something like 20 times 0.05. So I have 20 times 0.05 in my numerator all over 0 times 8 times 4. Okay. Well, this 0 in here is in the denominator. So this term is dividing by 0. So regardless of the numbers that I see there, that is going to be equal to infinity. So for this type of system, which is a type 1 system, regardless of how complicated the system it is, as long as it's a stable system, we're going to get an error, a position constant that is equal to infinity. Okay. And it doesn't matter the numbers, as long as it's stable, we're going to have that value. If we do K sub V, that's the limit as S approaches 0. So this is S now times 0.05 times 4S plus 10 times S plus 2 all over S times S squared plus 4S plus 8 times S plus 4. Now I can see that my S terms will cancel. And what I'm left with is, let's see, 0.4 all over 32. And that's the velocity constant that I'm going to have there. I get to cancel out an S. This is not a 0 or not an infinity number. So I can actually calculate some errors. So I'm going to do that in a second. Let's do our K sub A, our acceleration constant. The limit as S approaches 0, S squared times 0.05 4s plus 10 times s plus 2 all over s squared plus 4s plus 8 times s plus 4. And here's my s term. And so when I cancel everything out, I'm only going to be able to cancel out one of the s terms in the s squared term. So I end up with s times 0.4 over 32. As s approaches 0, this term goes to 0. So that is going to be equal to 0. So the only number, again, that is non-zero is, or non-infinity, is a unit ramp. So now I can calculate my error, or my steady state error. Again, as long as the system is stable, my steady state error here, ESS, is going to be equal to 1 over 1 plus k sub p. 1 over 1 plus infinity is equal to 1 over infinity, which is equal to 0. So for a unit step input, there's going to be no error, no steady state error associated with this problem, with this particular system. For my next case, which is my unit ramp, I'm not sure how that happens. Sorry about that. My ESS is 1 over k sub b, which is equal to 1. I don't know why it's a little slow. 1 over 0.4 divided by 32, which is equal to 32 over 0.4. Is that equal to 80, if I have that correctly? And then lastly, my parabolic error is 1 over k sub a, which is equal to 1 over 0, which is equal to infinity. And this work applies for every type of system, or for any type of system where if I have a type 1 system, ESS is going to be equal to infinity for a step. ESS is going to be equal to the limit as s approaches 0, s times GH for a ramp. And ESS is going to be equal to, I said infinity, 0, sorry about that, 0. And this is going to be equal to infinity for a parabolic. Okay, those are the steady state errors. Then I can also do my constant. My k sub p here is going to be equal to infinity for a step input. My k sub v is going to be equal to, I did this incorrectly, sorry, it's 1 over that value. So it's going to be equal to the limit as s approaches 0, s times gh for a ramp. And k sub a is going to be equal to the limit as, actually, no, not even the limit. It's just going to be equal to 0 for parabolic. This is for a system type from 1. And essentially, that was the answer we were looking for. So it says, find the steady state error for the following: 4-volt DC input, 2-volt ramp input, point whatever parabolic input. So let me go ahead and copy those over. So I did those generically. Now we'll modify them. Come on, gotta grab my snipping tool. There we go. Let's paste that over here. Okay. So A, it says find the steady state error in the case of P for 4-volt. It is still these values. For 4-volt DC input, that's considered a step input. It doesn't matter that it's 4 volts in magnitude. It's going to be equal to 0 and infinity. Same thing for C. So this is the answer for A. For C, here's my answer. Because for any parabolic input, it has no chance. The error is going to continue to increase. So I get that value. For a ramp input, the only thing that I need to do is multiply this number by 0.02. Okay. So remember how this is our ESS. So this here gets multiplied by 0.02. And this number here gets multiplied by 0.02. So your final answers were, let's see, is this erase or highlight? Here and here. Okay. Questions on that? Make sense? Don't make sense?
It makes
Yeah,
sense.
it does.
But I think I'm probably gonna need a little more practice at that.
Okay. Yeah, so it's a multi-step process to do steady state errors. Your step one, whoops. Step one is find GH. I guess even before, if you're going to be able to find a steady state error, so maybe even before that, so begin. Is it stable? If it's not stable, there's nothing you can do because the output is going to not be Bobo stable. So if it's not stable, then you can't even proceed on with the work. You're sort of stuck at the word go. There's no way to proceed because like that output is just going to continue to go to infinity. And no matter what you do for an input, the output is just going to continue to blow higher. So there's not even a point to analyze a system that isn't stable. If it is stable, you're going to find your GH, which again is our open loop transfer function. Once we have that, define or find, maybe a better one is instead of find, let's see, how about identify the system type. Okay, so you identify the system type, and that'll tell you, all right, if it's a type 0, then I only have to worry about doing any calculations for K sub P and ESS for a step input. Yeah, if it's a parabolic and a ramp, then I don't have to do any calculations. If it's a type 1 system, I only have to worry about doing calculations for a ramp input. The other two, the step input's going to be 0. The steady state error is going to be 0, and the parabolic is eventually going to go to infinity. If it's a type 2 system, then the first two systems are going to have a steady state error of 0, and then the third type, the parabolic input, is going to be one where I actually have to calculate what that value is going to be. So by identifying the system type, you it helps you to let's see, select corresponding K and ESS to calculate. I just continue to do that. I don't know what's going on. So what I mean by that, if it's a type 1 system, so let's start off with type 0. A type 0 system, you're going to calculate K sub P and ESS for a step. You should know K sub V, K sub A, and ESF for a ramp and a parabolic. Okay. If it's a type 1 system, you're going to calculate my velocity constant and my ESS for a ramp input. My K sub P, I know is going to be equal to infinity. And my ESS for a step is going to be equal to 0. So I have those two. And then my K sub V, my K sub A is going to be equal to 0. And my ESS for a parabolic is going to be equal to infinity. The last system type that we're going to worry about means you only have to calculate K sub A and ESS for a parabolic. My K sub P is going to be equal to my K sub V, which is going to be equal to infinity. My ESS for my step is going to be equal to my ESS for my ramp, and that's going to be equal to 0. Okay, so that's just sort of a summary of how to do the ESS work, but looking at it, sort of getting back into it with the approach. So it hopefully is a pretty straightforward process where you find your G of H, you get your system type based on that G of H, and then all you need to do is go to correct row, and then you pull out the parameters, and the correct row is specified by system type. So pausing for questions. Is anybody with me? Anybody? Making sense? Not making sense? This is important. If you don't talk, then I'll have to guess if you know it or you don't. So
Yeah, I think I get it. I just missed the open loop portion on that question of the homework. But yeah, no, you explaining it now helped my understanding for sure.
okay. Thank you.
Yeah, it was the exact same thing for me. Like, if I had been able to get past the first step, I would have been able to do the rest of it right.
Okay. Okay.
Yeah, I guess I'm in the same boat. If I got it better, or if I had a better understanding, I'd probably get the rest of it right.
Okay. So it sounds like where the confusion perhaps existed is that you had to use the open loop transfer function. Is that correct?
Yeah, that's what it was for me.
Okay.
Yeah, same here.
Okay. I just want to make sure. Because in the slides, I just want to make sure that if I need to adjust them or not. So this is the steady state error work. And you see here where we did the error signal, and we said that our error signal is R minus C, which is equal to this value. And then our steady state error is a limit function here, where we had an input over 1 plus GC GP. And then eventually we came up with a concept of a K sub P, where you can see that we moved the error signal to just be around, in this case, because it was a unity feedback, our feed forward gain, just my controller and my plant. It doesn't include that G over 1 plus GH. Was this clear enough looking back, or do I need to add more clarity now?
I think my confusion lied in the fact that that homework problem wasn't unity feedback, which, unless I missed on the slide, I think I just missed the placement of where we were like opening the loop or whatnot. So
Yeah,
Okay.
it's toward the end of the slides. And that's what I had been trying to use on it. And I think I just got confused trying to like use those last couple slides.
Yeah, so you can see over here, if we have a transducer that we don't compare it, we have to do a bunch of work to make it unity. So this is this actuating signal as opposed to our error signal. But all I was really worried about is, did you have an EA value? So if you did it this way, you would have ended up with the same result. It's just would have been a lot more work to be able to do that. And the problem is we didn't have the ability to move this pickoff point to this other side. So it would have been a little bit more difficult to go ahead and put that in there. Okay.
Yeah,
All
fair
right.
enough.
Go ahead.
No, I just said seeing it again, you know, it makes sense that but probably just missed it the first time through, but.
Yeah, you can always go to GH and just say that the error that I'm determining is this actuating signal error here that we have. So that's the error, the actuating signal error. Okay. Any more discussion that would be helpful in this topic, or? Now, did you guys have lab this week on this topic?
We did, yep.
Okay, good. Okay. All right. Let's get back to. Let's get back to, I don't know why this is open. Root locus. Okay, so the last slide, we did a bunch of work, right? To get everybody up to speed on how to do rectangular and polar, sort of polar math, right? Which is vector math essentially, to simplify it. And then we did this example where we were trying to figure out individually the magnitude and the phase of a transfer function at a particular pole location. And if that equals essentially 1 at an angle of 180, then that would be a valid root. We ended up seeing that this is 0.22 at an angle of minus 114. So that wouldn't necessarily be a valid root, but that's okay. We weren't necessarily checking. We weren't really using this to determine if it was a valid root. We were really trying to go ahead and do some calculations to see if we got this. Okay. So all these magnitudes and angles to get from -1, which you can see is a valid 0, to get from -1 to here, we did the calculation and we found out that that's equal to square root of 20 magnitude, and it has to rotate 117 degrees. To go from our next pole, our next either pole or root, which is at root at s equals 0, we have to go this magnitude and we have to rotate this angle. Magnitude is a square root of 25, and it had to rotate 127 degrees. We only have one more polar 0 to deal with, and that's this s plus 2. So we're going to go ahead and solve for this magnitude and this angle. Our magnitude is square root of 17, and our angle is approximately 104. And so now to get the total, to see what the actual value of our transfer function is in terms of magnitude and angle, we're going to do all the math for all those different magnitudes and angles and figure out if that's equal to 1 at an angle of 180. And when we divide the magnitudes, square root of 20 divided by 5 divided by square root of 17, we get 0.22. That's not 1. And then when we take 117, subtract 127 and 104, we end up with minus 114, not 180. So this we know is if we increase our value of K, we will not pass through the point -3 plus J4. Okay, so this is a MATLAB script file. You can go ahead and do that. And this is a way to show how to do what's called an inline function. So if you have this variable that you're passing at this value of S, you can go ahead and it'll substitute in our value for S anywhere it sees this S1. So basically it's saying, I've got a variable here, and this variable is going to be based on, or you can use that variable to solve for this equation for G. And then I plug in my value that I'm trying to solve for, in this case, S equals 1, into this expression. And that's the expression that we have here. And we calculate the magnitude and the angle. And this is just some fancier printing. I actually did this in MATLAB where I got a little bit easier. So let's bring up MATLAB. And I'll show you, because again, just because that's what it says on the slides, that doesn't necessarily mean it's correct. All right, so let me bring this over here. So here is my file. And again, I just cleaned it up a little bit to simplify it. I'm still using an inline function, but I just go ahead and do the phase calculations directly. So that's my root, -3 plus 4i. This is the equation for my transfer function, my g. Then I have my magnitude for g, just the absolute value. And then the angle, I multiply that by 180 over pi. So I'm going to run it. And then I've got to bring up MATLAB. And there is now, of course, it won't show it all the way. I'm sorry, 0.2169, 0.217 at an angle of -114.3, which is there, but then it is pretty much the exact same value I had by doing it manually, which is what we did at the last class. All right, everybody understand that process? Okay, so that's going to give us one of our rules, and we kind of know this already, but we know that the root locus has to be symmetrical about the real axis. And the reason why it has to be symmetrical is because we always have to have complex conjugate pairs. You can't have a plus J7 without having a minus J7. So that's our first rule that we probably have already thought about and already know. All right, your turn. I'll give you 5 minutes. I have 2:39. I'll give you to 2:45 to go ahead and give me these results. So 5 minutes. I'll check back in at 2:45. So I'm going to pause the recording unless people have questions. And then I will ask a volunteer to present their work in 5 minutes. So here we go. Okay. Ethan, would you be willing to give me the magnitude and angle for the pole at the 0 at s+3?
Are we just like plug the -2 plus j into the transfer function we have in there?
Correct. Just like what we did here, right?
Yeah, I have it like in rectangular form if that works.
I need it in polar form because it'll be better to see magnitudes and angles looking at this plot here.
I can do it right now. I have my MATLAB set up right next to me, so
Okay. All you have to
So-
do is abs and angle times 180 over pi. That should give you those numbers.
so the magnitude would be 2.2361, I believe.
No, I'm just looking for the pole.
Oh,
I'm just looking for I just want to know what this magnitude is and the angle that magnitude has to be at to go from here to here. So just that number right there.
oh, okay. So the one I found is probably the 2.23 at the angle of -153 is that the blue dot, and I have to calculate the distance from that point to the pole.
The 0 at -3.
Oh, okay. Then I might need more time, Paul. Sorry.
Okay, that's okay. How about Janelle? Would you be willing to help Ethan out?
I actually got tripped up kind of in the same way, so I'm not sure.
Okay. Let me do the first one then, and then maybe you can help, you can do the other ones. So our transfer function, and again, this is our GH transfer function, our open loop transfer function is equal to s+3 times s+4 all over s+1 times s+2. Now, we want to know what GH of -2 plus J is going to be equal to. And we're going to do it individually. We're going to do it one at a time. So the first thing you need to do is figure out what the magnitude and angle is of S plus 3 when S equals -2 plus J. So what is the magnitude of that? And what is the angle of that? Well, first thing I'm going to do is I'm going to go and get magnitude. This is going to be equal to 1 plus J. And this is the angle of 1 plus J. Well, hopefully I can see pretty quickly that this is a right triangle whose magnitude is 1 and 1 here. We know that this is 45 degrees, and this is equal to the square root of 2. So this here is equal to square root of 2 at an angle of 45 degrees. That's the first one.
Can I ask you a question, Paul?
Of course.
So what I did is I just plugged the whatever the S value that we have and just plug that into the transfer function, and I've got the result from that. So I just got the final result only, right? So I
Yes,
didn't.
you got the
Okay.
final result.
Yep. Okay. Yeah. Now it makes sense. Yep.
Yeah, what I'm looking for and what we just did is hopefully you can see that this here is the square root of 2, and this angle is 45 degrees. And you can also look at it graphically, right? Because I have to go up 1 and over 1 to get to that point from this -3. So you can see that that's a right triangle with a 45 degrees. And I think it's an isosceles right triangle, if I have that correctly. So that's how I end up with square root of 2 and 45 degrees. All right, Ethan, would you be willing to do the next one for me? The S plus 4.
All right. So magnitude 2.23 and at the angle of 26.
Okay. Owen, how about, can you give me S plus 1? Owen, can you hear me?
Yeah. I just don't know. I'm trying to figure it out right now.
Okay, I'll give you a minute. If you look in the chat, go ahead.
Yeah, I got the same answer as Joanna. It's
Are you
1.4.
sure you got the same answer?
I am positive.
All right, let's check it. So that's going to be equal to -2 plus J plus 1,
Yeah,
which is equal to -1 plus J, correct?
correct.
Now, if I take the absolute value of that, let's see,
Would your
I'm going to
angle
go
be flipped by any
m-
chance?
-1 in that direction. and +1 in this direction, correct? So this is square root of 2. And the angle I need to rotate is not minus 135, but plus 135. Because if I went minus 135, I would be down here, correct?
Yeah, I just saw there's no negative sign on my calculator, so yeah, that's what I got.
Yeah, if you ever get stuck, you can always just draw, you can draw the angles that way. So that's going to be equal to, if I'm correct, is square root of 2 at an angle of 135. Jacob, would you be willing to give me, let's see, S plus 2, evaluated at S equals -2 plus J? Jacob, can you hear me?
Yeah, I can hear you.
Okay. What do you got? Can you still hear me? Can everybody else still hear me? Am I still broadcasting?
I can hear you.
Oh, okay. Jacob, are you still there?
If you want, I can get, I believe I have the answer for this.
All right, go ahead, Tom, help him out.
Okay, so the answer I got is, you just want the angle, right?
Magnitude and angle.
Magnitude and angle. So I got, so the magnitude of 1 and the angle's 90.
Very good. And how he knew that, and you can correct me if I'm wrong, Tom, the way that he knew that is because it is -2 plus J plus 2, which is just equal to J. And we know that J is 1 at an angle of 90 degrees. So now we have all the magnitudes and angles for my GH of S evaluated at S equals -2 plus J. All my magnitudes and angles, I got 1.414, which is the square root of 2, at an angle of 45 degrees. I got 2.23 at an angle of 26.57. I got 1.414 at an angle of 135. And I got 1 at an angle of 90. So very good. Looks like we're getting a little bit of the hang of how to calculate magnitudes and angles. Now, here's the next step. What is the magnitude of GH of S evaluated at S equals -2 plus J? How do I solve for the magnitude of that? Eric, would you be willing to help us out on that? Hello?
I'm actually not entirely sure on this one.
Okay. Anybody want to help Eric out?
You
Mort?
just combine them.
Say more.
You just multiply the two, the denominator and numerator together and then divide by each other. You just solve that, simplify that out.
Almost. You multiply the magnitudes of the terms in the denominator.
Oh, yeah. So then the top row, you'd be adding the angles. And then once you combine the two lower ones and subtract those angles.
Yep. So that's the magnitude. We did that one. Now let's add on the angle as you suggested.
Yep.
Okay. So
Good
now
enough.
you're exactly right. We add the angles that are in the numerator. And we subtract the angles in the denominator. So let's see what I end up over there. Let's bring up MATLAB. So I have 1.414 times 2.23. We'll do that again because I forgot to divide by, divided by 1.414 times 1. So 2.23. So this is 2.23. And my angles, 45 plus 26.57 minus 135 plus 90. Minus 153.43. So my final answer for GH of S evaluated at S equals -2 plus J is equal to 2.23 at an angle of minus 153.43. Ethan, can you correct me or not correct me, but can you confirm that the numbers that you did originally, that the first numbers you gave me, are these relatively close to what you provided?
It is exactly the same up to 2 decimal points. Yes.
Okay. So according to Ethan's work, this checks out. So we did it by brute force, doing it manual way. And I'm assuming Ethan, and Ethan can correct me if I'm wrong, but I think what Ethan did is if you do it here, okay, if you do it with the inline functions, the approach that we had, S1, which is our root that we're trying to solve for, -2 plus I or J, right? Same thing. Our inline function, S plus 3 times S plus 4, that divided by S plus 1 times S plus 4. Then I get the magnitude of our gain. And then our angle of our gain, again, multiplied by 180 over pi. So I'm going to run that and bring that into, actually, you know what? Tell everybody I need to keep myself honest. So let's put that in there. So everything is cleared. And let's go back through. And does that check with what Ethan said and what we calculated? 2.23, you can see there's a little bit of rounding, 2.2361, and the angle is minus 153.43. So the approach that we did, and again, that approach for adding or multiplying or dividing complex numbers that are in polar coordinates is super, super helpful, especially when you look at power systems and you're trying to calculate things. That's why we use impedance magnitudes, and we can do angles, we can subtract angles. It gives you sort of an intuitive feel of what's going on. But we're doing it here in root locus because it makes things work really super duper well for us. Okay. So everybody feeling more comfortable with this stuff at this point? Uh-oh. Is anybody feeling more comfortable?
Yep, so far so good.
Okay.
Yeah, I think I'm in.
Okay. So if we do it over here, we felt pretty good about doing that. All right. So let's just make sure that each one of those, and you can, I encourage you to check. This one was the easiest one. Hopefully you can see it just has a magnitude of 1 and 90 degrees. This one is a little bit harder. And this one's a little bit harder. But if you check the angle calculations we did, I think we said that this one was 135. And I can't remember if that one was 53. I don't remember exactly what it is. Moment can't have been 33. This one was 26, I believe. So you can take a look and see if those magnitudes and angles are approximately what we expect them to be. All right. So one of the things that I want to highlight is, remember what we did. We're only doing the phase and gain of the open loop transfer function. And if you recall, back at the beginning of last class, when we developed our root locus approach, we had, sorry about that. We had our characteristic equation was G over 1 plus GH. If we had a variable value of K included in there, we had that value of K, which meant that we also included it over there. And the denominator here is our characteristic equation. Well, what we said was 1 plus k, there's a numerator and a denominator term, right? And then we put that under a common denominator. We had GD, HD plus K, GN, whoop, GN times HN. And this term that's over here in the common denominator ends up getting multiplied. So we end up with this over here. But that gets inverted and multiplied and end up getting moved up to the numerator. So we really don't care about it. We really only care about this transfer function here, that we have this characteristic equation, because there is going to be a numerator associated with this, but that's just going to end up dropping out. That's going to end up canceling out. So what we have is GD, HD plus K, GN, HN. And if we recall, our K is going to be greater than 0, but less than, whoops, I did it the other way around. No, I had that right. I always have to go back to when I was in grade school, whatever, is the alligator mouth, right? The alligator mouth always opens to the bigger of the ones. So if K is 0 or very close to 0, these are the only two terms that I have. So those are the denominator terms for both the G and the H. These are the original poles of the system. Okay. As K is allowed to increase greater and greater and greater and greater, what ends up happening is these terms get to be a smaller part and these terms get to dominate. These are the zeros of the system. So looking back at our plot, if we wanted to actually find our root locus map, we're going to start at a pole and end at a 0. So we start at a pole, which means we start here. And we also have to start here. At some point, they're going to get to each other, and we don't know that number. We have to figure that out. They're going to break away, and then they're going to jump back, and this is supposed to be symmetrical. It's going to jump back onto the real axis, and then it's going to end over here. So we're starting at the roots for the poles and ending at the zeros. Okay. And so hopefully what you see with this one, and it's really helpful to look at this one because we have two poles over here. So they're starting there, but they can't terminate. We would need a 0 to terminate. So what ends up happening is we have to leave this real axis and we have to go complex until such time that we get back onto the real axis. And as K continues to increase, we start to get closer and closer to those zeros that we have. And again, that all goes back to finite poles and finite zeros and infinite poles and infinite zeros. You can see the number of poles of finite poles, or number of finite poles. Oh boy, my spelling is way off today. Sorry about that. Equals the number of finite zeros. So we don't have any infinite poles, which is a good thing because this root locus plot doesn't continue to go on forever and ever and ever and ever. It stops at -4, just like it stops at -3. If for some reason this pole didn't exist, then this would continue forever going out that direction, and it would approach a 0 at s equals infinity. Okay, so that is sort of the root locus. And this point right here, we know we didn't go on that point because if you remember for our practice, we ended up with, let's see, it was 2.23 at an angle of -154. Well, if we go back to our work for our root locus, we know that 1 plus K GH must equal 0. Because if it's a root locus, it's a plot of all the roots for as this value of K. Then when we plug in a value for S over here, it has to equal 0. So K times GH is equal to -1. So the magnitude of KGH has to equal 1, and the angle of KGH has to equal plus or minus 180 degrees. Okay, so if we really wanted to boil down to it, we can see that K would have to be, K is going to be equal to 1 over GH. That's a hard one to solve for because we need to know what the magnitude of GH is going to be equal to, but the angle one is pretty easy. So I knew that that point that we were just looking at wasn't a valid point because its angle was not -180. Had that angle worked out to be -180, then we would have said, yep, we have a possibility of being a pole at this particular location. And then the way that we know if this is equal to 180 plus or minus 180, then what we do is we say K is going to be equal to 1 over GH. So we plug in our value for S over here, we get the magnitude of that, and then that gives you that value of K when it crosses a valid point. Okay, so that's kind of the summary or the discussion of root locus. So let's set up the root locus here. So we have a simple block diagram here where we have a feed forward G and a feed forward H. We have a variable value of K. And remember, that's a real number, a positive real number, which means it's a scalar number and it doesn't have a complex term with it whatsoever. So K is never going to add an angle to it. So K greater than or equal to 0 all the way up to infinity. That's our assumption that we're going to do. Our closed loop transfer function is going to become KGH. That's our open loop transfer function. You remember the ... over here means I couldn't care less what's happening in the denominator because I'm just looking for roots. I'm only looking for response characteristics of my system. So I'm only focused on what's happening down here in the denominator. So here's my characteristic equation. I'm going to set that equal to 0 for my root. And then I have to make sure that that evaluates. So my KGH equals -1. What is the magnitude in the gain? Magnitude of K, for it to be a valid point, is 1 over GH magnitude. And my angle is going to be plus or minus 180. It could also be plus or minus 3 times 180. So that has to do with the number of, we'll learn about the differences between poles and zeros. We get that value. And it's going to be always odd multiples. It's not going to be even multiple, because an even multiple of 180 is 360. And that's not going to be equal to plus or minus 180. So that's why the plus or minus 3, if you get this to be 540, that's just going to be equal to 180 degrees. All right, so this is just more summary, right? So 1 plus K, Z, poles and zeros. So if I bring this up into the numerator, I set that equal. If K is equal to 0, we get our poles. Then that's the poles of GH. If K equals infinity, we get our characteristic equation dominates with our zeros. That's the zeros of GH. And here's the last thing I want to present today, because we're just about out of time. Our root locus starts at the open loop poles. So again, just the G times H. And it ends at our open loop zeros. So you're going to hear me say that a lot. Start at a pole, end at a 0. Start at a pole, end at a 0. When you're trying to define or develop a root locus plot, it's imperative that you keep that in the back of your mind, because your plots are going to look odd. They're not going to make any sense unless you have that starting at a pole and ending at a 0. So that's why when you look back at this plot here, right, I started at poles. I didn't show the arrows. I should have showed that, but I'm going away from my poles, but I did show my zeros here and here. And so this one is going up in this direction, going down over in this direction, and continuing until it gets back onto the real axis. And so one of the things we have to do is we have to think about what are called break-in or breakaway points. This is a breakaway point. It breaks away from the real axis, and then it breaks in to the real axis at a different location, which we will cover at our next class. So questions? I'm trying to really make sure the math makes a lot of sense here. So I'm trying to go and give a lot of, practice on how to do some of the math equations, because I recognize we don't take vector calculus as EET students. And this is, depending on what kind of experience and exposure you've had, could be a little challenging. So if I'm going too slow, I apologize. But I just really want to make sure that everybody has a pretty good handle on how to do these calculations, because it will help us when we're understanding all these points and breakaways and all that stuff. Okay, any questions? All right, well, if there are no questions, have a great day, and I will see you all on next week. Take care, everyone.
Hey, Paul,
Thanks.
Yes,
I have a question that has nothing to do with the class.
okay. Let me stop recording
Um,
then.